Hello, my name is Steve Miller. I'm a math professor at Williams College, and I am going to be talking today about some introduction to some basics of probability, and with one of my assistants. And it is a pleasure to thank the Journal of Number Theory and the Teachers as Scholars program for help with these lectures. All right, so what is our goal today? Our goal is to talk about some important functions in probability, the factorial function and the permutation function. And so we're going to see what they are. We're going to get a little sense of how they're used. And the goal is to build up to a later lecture. We're going to apply this to one of the most interesting and entertaining games to play with cards. What game is that? What game do we like to play? We're going to play it with bridge. We're going to learn how to figure out some trump splits and the likelihoods of various things. So some basics of probability. We're going to choose problems mostly from card games or from dice. And what do we mean by probability? Well, when you hear the phrase probability, you should be thinking, like the odds of something happening. Percentage is a great thing. What percent of the time does this happen? So in many situations, each event is equally likely. And if you're in a situation like that, it's very easy to figure out the probability that something can happen. You just look at the number of ways your event can happen, and you divide it by the number of ways that something can happen. So let's do the following example. Let's consider that we roll up there a die. So if you roll a die, what can you see on a die?
1, 2, 3, 4, 5, and 6.
Right. And if the die is fair, do you see all numbers with the same frequency, with the same probability, with the same chance? See how many words we have for the concept? So they're all equally likely. So here are my first two questions. What is the probability we roll a 6? And what is the probability we roll an even number? So I'm going to pause the recording and let you try to answer that. Welcome back. So assistant, what is the probability we roll a 6?
Probability we roll 6 is 1/6 because there are 6 different choices.
And only one of them is a 6.
Correct.
What about the second one, the probability we roll an even number?
Well, since 3 of them are evens, the answer would be 3/6 or 1/2.
Exactly. And so in situations like this, it's not too bad to find the probabilities of events if we can just list all the possibilities without too much trouble. So now I want to introduce the factorial function. And the N and the exclamation point does not mean I'm excited, although I am truly excited. It doesn't mean the sentence has ended. That's actually how we write the function. We use an exclamation point to talk about the function.
Because we love factorial.
We do love factorials. And so we would write the factorial of an integer by writing the number and then the factorial. So 3 factorial would be the factorial of the number 3. 5 factorial would be the factorial of the number 5. So there's a nice meaning to it. The factorial function is the number of ways to arrange objects when order matters. So n factorial is the number of ways to arrange n objects when order matters. So if we have just one object, A, how many ways can I order it?
A.
So how many ways? One way. But if I have 2 objects, A, B, how many ways can I order them? 2. I could have A first and then B, or B first and then A. Now, if we have 3 objects, A, B, C, there's 6 ways. I can go A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, C, B, A. Cab. And so my question for you is, why did I choose to write them in this order? So I'm going to pause the video so that you and we can think about that for a moment, if you want. All right. So we wanted to make sure we don't miss any cases. That's why we did it like this. We're looking at all the ways where A is first. So there are 2 ways when A is first. I can go A, B, C, or A, C, B. And that's these 2 things here. Then I look at all the ways when B is first. And I can have BAC and BCA and so on and so on. So let's try this with a picture. So here's the possibilities. I do A first. Here I do B first. Here I do C first. Then I choose B, or here I choose C. Here I choose A, or then C, or A and then B. And then finally, the last one. And there's no choice for the last one because I've got 3 people. I've already chosen 2, so only 1 is left. And so this path would be A, B, C. So I've done it red, purple, blue. This path would be A, C, B, and I've done it red, blue, purple. So I'm having the red person associated to A, the blue to C, and the purple to B.
Why don't there are the different colors with the different,
different shapes or styles
kinda.
or positions.
Because it looks like, wait, is the red one putting their
Looks like-
hands on their heads, or is that their hair?
I think that's their hands on their head. But it could be their hair if they have no arms.
No, because then
No, those could
right
be,
there could
be,
be the arms.
yeah, could be right. I think it's a little low for their arms. But when you look at all this, this is a really good way so that we don't forget any cases. Now, what if we do something a little bit harder? How many ways do you think there are to order A, B, C, D? There were 6 ways to order A, B, C. So I'm going to pause and let you think about how many ways we could order 4 elements. So let's look and try to count how many ways there are to order 4 elements. So there are 4 choices of what could be first. I could have A first, B first, C first, or D first. I'm going to choose to look at the branch when D is first. Why? Well, 2 slides ago, you had this beautiful picture of how we can order A, B, and C. And here are the 6 possibilities. So there are 6 ways to order A, B, and C where order counts. And then I can just put a D in front of them. And this is 1/4 of the whole tree. Then there's going to be a tree when A is first, and I have to order B, C, and D. There's going to be a tree when C is first, and I have to order A, B, and D. And finally, there'll be a tree when C is first, and I have to order A, B, D. So each one of these has 6, and then there's 4 possibilities for which goes first. So it's 6 times 4, or 24. So the factorial function grows very quickly. So here is a plot of the factorial function up to 5. So 5 factorial is 120. It's very high, but you can still see 1 factorial and 2 factorial down here. Here, I've extended the plot up to 9 factorial. 10 factorial is already off the chart, more than 800,000. Here is 9 factorial, about 400,000. It's about 9 times 8 factorial. And look, these numbers here are so small relative to this, you can barely see them. Now, the number of ways to order a deck of 52 cards is 52 factorial. It's basically 1 followed by 68 zeros. There is a tremendous number of ways to shuffle a deck of cards. It is unlikely that anybody has ever shuffled the deck of cards and had it equal another person's shuffle if the deck was randomized. So if 2 people were to shuffle a deck, it's unlikely that they would get the same shuffle. If you look at all the shuffles throughout human history, it is unlikely that any 2 have ever been the same, because there's just been so few shuffles. To put things in perspective, there's about 10 to the 80 or 10 to the 90 objects in the universe, and we're already at 10 to the 68 with just shuffling a deck. If you look at the ways to shuffle the alphabet, which we use in some codes, there's about 26 factorial, which is about 10 to the 26. So now we have an interesting question. 4 factorial is 24, 3 factorial is 6, 2 factorial is 2, 1 factorial is 1. So what the factorial function is going to be is it's going to be the product of all things all the way down. Okay? It's an interpretation right now. We haven't really given that formula, but it's an interpretation. Here's my question to you. What should 0 factorial be? How many ways should there be to order 0 objects? I'm going to pause so that you can think. So I'm back with my assistant. So how many ways are there to do nothing? Can you do nothing 2 different ways? No, because then you'd be doing something. So how many ways are there to do nothing? 1. Most of the time, you are still doing something. If you think you are doing nothing, just sitting on your bum watching TV,
Wrong.
you're actually doing something. You're watching TV on your bum.
You're watching TV, you're sitting on the couch, you're breathing.
You're doing something. Oh, that's right. Remember to breathe, those of you at home. Okay. So 0
We're never
factorial.
doing nothing because we're always breathing.
So we're going to define.
Even if we're dead,
Yeah, even,
we're being dead.
Yep.
Or lying in
So you're still doing something. So we define 0 factorial to be 1. It turns out that this is a useful definition. It's similar to when we studied primes. We decided that 1 is not a prime. That was useful, and that meant that every integer could be written uniquely as a product of primes in increasing order. It's useful to define 0 factorial to be 1. It is a definition. Okay, so here is a nice property of the factorial function. If you know a value, the next one is pretty easy to get. 4 factorial is going to be 4 times 3 times 2 times 1. It's the number of ways to order 4 objects when ordered. How many choices are there for the first object? 4. Now that we've chosen the first object, how many are left for the second object? And then how many for the third? And then the last one is forced. Now notice that 4 factorial, 4 times 3 times 2 times 1, is the same as 4, let's put in parentheses, 3 times 2 times 1. What is 3 times 2 times 1? 3 factorial. So 4 factorial is 4 times 3 factorial. So we've written it grammatically as an exclamation point for the factorial function followed by a period. You could actually be excited to have the exclamation point followed by the exclamation point, but it turns out in mathematics, 2 exclamation points is the double factorial, which means something else.
What is a double factorial?
It means every other. So 4 double factorial would be 4 times 2. 5 double factorial would be 5 times 3 times 1. So similarly, 5 factorial is going to be 5 times 4 times 3 times 2 times 1, or just 5 times 4 factorial. More generally, if we have n plus 1 factorial, it's n plus 1 times n times dot to dot times 3 times 2 times 1. So we put parentheses as before, and we have n all the way down to 1. So just n plus 1 times n factorial. So if you've seen Fibonacci numbers, this is another example of a recurrence relation where you get the next value from knowing the previous. For Fibonacci's, you need to know the previous 2, and then the Fibonacci was next. So it goes 1, 1, 2, 3, and what's 2 plus 3? And what's 3 plus 5? And 5 plus 8, and so on and so on. The factorial function is a little bit easier. You only need the previous value. You don't need the previous 2. All right. So now, do you want to do more, or do you think this was good for today? Let's pause it. So we'll do the next function tomorrow. We're going to end with a question. What was your question?
How do you multiply 0 to get 1?
So we have to somehow adjust things. So 0 factorial, notice how we do all the multiplication all the way down to 1. We basically define 0 factorial to be the empty product. We define the empty product to be 1. Just like we define what would you define an empty sum to be? A sum of no terms would be, and a product of no terms is, nope, a product of no terms is 1. If you want, one way to think about this is 1 is the multiplicative identity. If you multiply something by 1, do you change its value? What do you add to something not to change its value?
Yeah.
So that's another reason why we like to do stuff like this. So we will stop here for today. Have a great day. I hope you have as much fun as you can in these conditions. Look for the opportunities, and we'll do more math tomorrow.